Hello friends and welcome back to my channel. In today's video, we'll be learning about light energy for class 8 ICC syllabus. This is the second part of this series. Kindly watch the first video for better understanding. Now, let us look at what we will be doing in today's video. We'll be learning about the laws of refraction, also called Snell's law. We'll be learning about refractive index and how to calculate the refractive index of a medium. We'll be learning about the effects of refraction and why does view from side change the depth of a substance. First, let's learn about Snell's law. Snell's law is also called laws of refraction. It consists of two statements. The two statements are given here. Let me read it out for you. The incident ray, the normal and the refracted ray at the point of incidence all lie in the same plane. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant. That is, sin I by sin R is a constant. Now, Snell's law consists of these two statements, and if there is a question asked like state Snell's laws or state laws of refraction, you need to write these 2 points as your answer. Now, I'll be explaining the first point a little later. Let's move on to the second statement. It states the ratio of sine of angle of incidence to the sine of angle of refraction is a constant. Now here sin I is sine of angle of incidence. The ratio of so that probably means that this is a division, right? It's a ratio, so it's comparison to the sine of angle of refraction, that is sin R is a constant. This means that sin I to sin R is a constant, that is the value always remains the same, it does not change. Let's say angle of incidence or angle of refraction can increase or decrease, but the sine of angle of incidence to the sine of angle of refraction, that is the ratio between these two, will always remain constant, it will not change. Now this constant, that is sin I by sin R, the constant is represented by this symbol. We call this symbol as mu. It is also a refractive index, to which I will be coming back a little later. But for now, just understand that the ratio of sine of angle of incidence, sin I, to the ratio division to the sine of angle of refraction divided by sin R is a constant. That is, its value will not change, it will remain same always. And this constant is denoted by this symbol, which is called mu. Now let me come to the first statement. The incident ray, the normal and the refracted ray at the point of incidence all lie in the same plane. Now let us look at this diagram. Now here we have a surface that divides two mediums. So now if this is the incident ray, the refracted ray and n dash is the normal, then the incident ray, the refracted ray and the normal at the point of incidence, the point at which the incident ray hits, this is the point of incidence, all lie in the same plane. Can you see that? The incident ray, the refracted ray and the normal at the point of incidence all lie in the same plane. These two are the laws of refraction that you need to learn. I hope this is clear. Now let us move on to refractive index. What is refractive index? As I said earlier, the second law of refraction is just the refractive index. Let me read it again for you. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant. As I said, this constant is represented by this symbol called mu, and it is known as the refractive index. Now refractive index is also the refractive index of the second medium with respect to the first medium. Now here, this is, please pay attention, this is how you calculate the refractive index of a medium. Now refractive index, we need to find let's say of the second medium, right? So mu, that is refractive index, is equal to the speed of light in the first medium. First medium, always we take it as air, but it depends on the question of course, but we take it as air, and speed of light in the second medium. This second medium is the medium of which the refractive index we are supposed to find. That is the second medium. Speed of light in the first medium is with respect to, in the question you will get it, with respect to and divided by speed of light in the second medium. That is the medium in which you are supposed to find. So it is known as the refractive index of the second medium with respect to the first medium. So the refractive index we are supposed to find is of the second medium. So we put it down, the speed of light. This is very important. We should write the speed of light in the second medium, and on top we write the speed of light in the first medium. Now let me give you an example which will make this more clear. Now, let us learn how to calculate the refractive index of a ray of light which travels from air to water. So, from here it is very clear that we are going to find the refractive index of water, right? Now, here, as I said earlier, refractive index is always sin I by sin R, which is a constant. This constant is refractive index. Now, refractive index is equal to, as I said earlier, speed of light of the first medium. Here the first medium will be air. Now, why is the first medium air here? Because we have to calculate the refractive index of a ray of light from air to water. So the refractive index that we are supposed to find is of water, but along with that they have given us air. So air is what we need to write on top, that is speed of light in air, speed of light in the first medium to speed of light in the second medium, which is water, speed of light of water. And after writing this, now speed of light in air is 3 into 10 raised to 8 ms per minus 1, and speed of light in water is 2.25 into 10 raised to 8 ms per minus 1. Now we do normal division here, score out these two, and then we get 3 by 2.25, which is 1.33, or we can also write it as 4 by 3. Now this is the speed, the refractive index of water. What is the refractive index of water? It is 1.33. Always remember, refractive index does not have a unit. It has only value. Now this is the value. We do not have unit. Unit in the sense gram, kilogram, meter, centimeter. We don't have all that for refractive index. It is just the value. No unit for refractive index. Now, this is how you calculate the refractive index of a substance. That is, refractive index of water is speed of light in air divided by speed of light in water, which will give you an answer, and that answer is the value. It does not have a unit. Very important. Let us move ahead. Let us learn how to calculate the refractive index of a ray of light which travels from air to glass. Now if you want, you can pause the video and try to calculate it on your own. Now how do you calculate this? Sin I by sin R is a constant. So here speed of light in air, we write that first, by speed of light in glass. So speed of light in air is 3 into 10 raised to 8 ms per minus 1, and speed of light in glass is 2 into 10 raised to 8 ms per minus 1. Now as usual we divide, so we score it out and we write 3 by 2, which is nothing but 1.5. So refractive index of glass is 1.5, and as I said earlier, does not have a unit. It's just 1.5. It's just the value. I hope this is clear. I hope you have understood how to calculate the refractive index of a substance with respect to air. Now if there is a question to calculate refractive index of a ray of light from glass to water, how will you do that? As I said earlier, medium 1 by speed of light in medium, first medium by speed of light in second medium, and then you score out and you get the answer, right? I hope you can do it, and If any doubts, kindly let me know in the comments below so that I can help you out there. I hope this is clear. Now let us move on to the effects of refraction. What are the effects of refraction? Now this is very important. You need to understand how to look at this. Now let's say there is a beaker in which we have filled water, and there is an object at O. Okay, let's say it's a coin or any substance, any object at O. For now, let's take it as coin at O, and we are trying to look at that substance from, this is air, right? So it's rarer, from a rarer to denser medium. Now, when we try to look at a substance from rarer to denser medium, the depth decreases. Instead of looking at the object here, we can see it as at I. Now, this is the effect of refraction. Why? Because when light travels from water to air, it's from denser to rarer medium, right? And so the ray of light refracts here. That is why here we don't see the object. When an observer is looking from air or from the rarer medium, the observer does not see the object at O, rather sees the object at I. So this is not the real depth, but this is the apparent depth. See, AO is the real depth, but AI is the apparent depth. That is the depth that is seen by the observer, but it is not the real depth, right? So now here it is due to effects of refraction that the ray of light here refracts, as you can see, and the depth seems to be comparatively lesser than the real depth, right? The real depth is supposed to be AO, but the depth AI is lesser. It is because the ray of light refracts that the depth seems to be less. This is the effect of refraction. I hope this is clear. Now let us look at why does view from side change the depth. Again, this answer to this is effect of refraction. It is because, look at this, for example, the coin is here, right? So you're supposed to see the observer is supposed to see the coin like this, but the ray of light refracts over here due to, of course, it's rarer to denser or denser to rarer. That is why it's rarer to denser. So that's why the ray of light refracts, and therefore the real depth is not the depth that the observer sees. It's comparatively lesser, right? The apparent depth, this is less, right? It should be this, but this is the real depth, but the observer sees the apparent depth. Why? Due to effect of refraction. It is due to the change in speed of mediums that the ray of light refracts, and there is a refraction there. And the depth seems to increase or decrease. It can, if it is from rarer to denser, the depth decreases, whereas if it is from denser to rarer, then the depth increases, right? So now here let us look at this example as well. Here we have an empty glass, and when we put a pencil inside, we see it just like that. But in the same empty glass, if I fill water and if I put the pencil, then the vision I see or the view I get is not like this, right? It's like this, and this is side view. When I'm looking from the side, when the observer is in the side like this. Why does this happen? Again, because of effect of refraction, because of change in speed of light in the medium. Now here we have air and here we have water. We know that the speed of light changes from rarer to denser, and that's why the ray of light refracts at this point, right? You can put the incident ray, refracted ray, normal, and the plane boundary, everything, and you can see that the ray of light is refracting at this point, and that's why we see the observer sees the view as this, right? So that's why side view changes the depth of the substance or object. I hope this is clear. If you have any doubts, please let me know through the comment section. I hope you have understood the teaching. Thank you so much for watching. Let's meet again in another educational video. Till then, thank you and happy learning.